Hi, students. Welcome to the chapter of Electromagnetic Induction. The purpose of the mostly academic UTME and SSA preparatory class is for maximum in-depth of knowledge in minimum possible time. And the purpose of all this checklist is for quick revision, shorty concepts, and to actually give you more light to what you have studied in your classroom. And if you have not studied, I believe what I'm going to say is enough for you to understand the concept. Like I said, I'm engineer Udi. I'll be taking you through some certain questions in electromagnetic induction, which I believe in one way or the other you might have studied in your junior classes. So because this is an O-level set of questions, I will only limit myself with the foundation, which is what you need to pass your examination. Let us start with the first question. If you find it interesting, consider subscribing to the channel. First question says, a coil X, this is the coil, is moved quickly away from the end Y. That's in the direction in which this is going. Of a stationary metal bar, with a stationary metal bar, and a current then flow in X as shown. Direction of the current starts flowing according to the word coil here. Then dash. The bar is not a magnet. B, Y is a North Pole. C, Y, the current in X is constant. D, Y is the South Pole. Then E, Y repels the coil X. To understand this, we must understand what we call the Faraday laws of electromagnetic induction. There are two laws of electromagnetic induction. The first one is called Faraday law. Listen, which is more like Faraday's experiment, which I know, I believe you might have studied. So the Faraday's law of electromagnetic induction, the first one says, whenever there is a change, I'm just writing, whenever there is a change in the magnetic flux, in the magnetic flux, linking a circuit, an electromotive force, which I write as EMF, is induced, which is proportional to the rate of flux, linking the circuit. So we are talking about a kind of induced EMF and induced current. So what the law is actually explaining to us, for those who don't have an idea about it, is that when there is a change in the magnetic flux, we've talked about magnetic field, electric field, and force carrying conductor, or force on the current carrying conductor. Now, we were able to tell you that the flux, the total flux, the magnetic field, the total flux is given as product of the what? Magnetic field is multiplied by the area. We've talked about that. But not to waste our time, now we're able to talk about the direction of magnetic field, which is more likely perpendicular. It can be in field, and as well, it can be outfield. Based on what you are supposed to know. Shorty concept. You don't need to waste your time. What Faraday is trying to explain to us was best explained later by the second law of Faraday of electromagnetic induction, I would write as EMI. The second law is now called Lenz's law, which is the continuation of what we talked about. When the relative motion of a particular what of a coil is stopped, electromotive force, induced current, induced EMF is generated. That is what Faraday is telling us. Now, this is a magnet. Let it be known. And when the magnet is moved, the motion of the magnet is moved towards the side of the coil. Now, one will be stationary, the other will be moved, or both of them cannot be stationary if you want to produce an induced EMF or an induced current. And there is no battery, as you can see. Battery is not connected to this. That is what we are talking about EMF. And most importantly, look at the direction. Now, if this coil is moved away from the magnet in this direction, what we're trying to say is that you can see, just like if I'm moving this thing towards the air, it's just for you to understand it's very either I move this away or I move this one towards it, they will produce the same what induced EMF or induced current. Now, we know flux will be generated. Flux are combination of different line of force. So I can say the flux will increase. And as the flux is increased, using the right hand thumb rule, I always tell you that's the best formula to use. Right hand thumb rule. Or basically what you've talked about, like Maxwell force field, whatever. Now, as I'm moving this magnet close to the coil, or I'm moving the coil away from the magnet, the flux is what is increasing. As the flux is increasing, now point your finger, as in just really, you can just use your right hand now. Open your right hand as I speak. Apologies, my camera is not on. Now, just drag your finger into the forward direction, like you are moving something towards. Where your finger points, you can see your finger is pointing in forward direction. That means you are talking about a kind of field that we call what? In magnetic field. So your finger will tell you the direction of the field. And now, as you move the finger, now cross that thing as if you are crossing a cord. Move those fingers like that, as you move them in a cord in an anti-clockwise manner. Because when you go inside with your finger, you move your finger in an anti-clockwise manner. And when you move your finger in an anti-clockwise manner, you can see the direction of the fluid of the coil. The coil direction is moving in a kind of what? You just have to be careful. Now, the direction of this coil, we need to look at the arrow. Now, if you are talking about infield, I have explained this thing to you time and time again. I wouldn't want to situation where the students are mixing the answer here because you need to be very, very careful. Very, very careful. Now, infield means what? You are talking about a kind of coil which you call the North Pole. For example, North Pole. When I say North Pole, North Pole, North Pole is up upward, you know that. Then the direction of the field is always moving anti-clockwise. Always keep that at the back of your mind. Now, when you are moving from south to north, this is what I'm saying now, because most of you don't understand this. Now, I am moving this thing away from it. If I move the magnet close to this, you should understand that normally if I'm moving the magnet and the direction of this thing is going clockwise, you can see the way this thing is going, it's going like this. So that is point. This is the point. It's moving like this. We can see the direction. It's moving in a clockwise movement. This is clockwise. So what we say is clockwise. That's why this short form. I think this will help you. Clockwise is south pole, whereby anti-clockwise is north. That is what we are talking about now. At this point, you can see we are moving this. And now, in this case, if I'm moving this towards this, the magnetic flux will be increased. But if I'm moving it away from this, because here I'm moving the coil away from the magnet, it will be opposite. Now, in this case, I'm showing you now, the coil will be infield and you expect a kind of anti-clockwise movement. The coil will be moving in an anti-clockwise as I move the magnet very close to the coil. What I'm trying to say is that before EMF or current is induced in a coil, one of these stuff must be moving. Both of them can't be stationary. So EMF cannot be generated, induced EMF cannot be generated, or induced current cannot be generated inside the coil if both the magnet and the coil are stationary. That is a basic point. You have to keep at the back of your mind. So my point now is in this case now, if I'm moving this magnet close to the coil, I'm going to have a kind of anti-clockwise movement, and the arrow will not be down here. The arrow will be down, up, up, up. And what that is telling me is what? It is a north pole. But in this case, it is opposite of what I've done. You can say I'm moving this one away. So if I'm moving this one away, you expect the direction of my field, the flux, the magnetic flux here, you expect it to what? To be reducing. because the flux for the coil is moved away. So if it is reducing, you now expect the direction of what induced EMF to move in opposite direction. That is what Lenz later told us. Lenz law states that, let me write it in language, that Lenz law now states that the direction, important fact, of induced current, either induced current or induced EMF, induced current moves so as to oppose, what opposes the change producing it. So induced EMF or induced current is always moving in such a way that is what? Opposing the direction of current generated. Now, if I move magnets close to the coil, flux increases, I'm going to see a kind of what? Clockwise movement. That I said anti-clockwise movement, which means the direction of what I have here will be the what? The north pole. That is if I'm moving this towards the magnet. I'm going to have north pole. For example, I have south and north of magnet. For example, bar magnet just always go to have polarity. So if I'm moving this guy very close, if I'm moving this stuff very close to the coil, like I said, you expect what the particular what the kind of what I told you anti-clockwise to what to set in. Now, if anti-clockwise sets in, the direction of force will now oppose the direction of the current. Current will be inducing and it will be moving upward, which is not go. So what you expect here is what the direction of current at this point will what not go. Why? Because it will produce a kind of anti-clockwise using my right hand on the. But if it is opposite, I always tell my students in classroom, you don't need to waste your time. Once you know one, the other one will be opposite of what you are going to tell. So I said, if I'm moving the coil close, the magnet close to the coil, I'm going to have a kind of what? Anti-clockwise, which is not pole. North pole will be generated at the side of the what? Of it. And because of that, North pole what? Repair. So in this level here, you understand what I mean by this. You expect what? Like post repair or like attract. So you expect what? They want a repulsion to occur between the coil and the what? In the magnet. But if I'm doing the opposite, which is this question, you can say I'm moving this one away. If I'm moving it away, it should be opposite of what I just said now. That is just what we are talking about now. If I'm moving this away, now I'm moving this away from it. And as I'm moving this thing away, you can see this is going away, the flux will be reduced. And because the flux is reduced, this is producing at the point here, wherever I'm moving, this is downward. You can see down is what? South. Down is south, up is what? North. We've talked about that in magnetic. This is north. And this is almost what? South. This is north. This is south. So keep that in mind. Down is south. So this particular point here, if this is moved away, the coil will produce the kind of anti-clockwise at the terminal here is south. Then where the bar magnet is will be what? Will be opposite. So always keep that in mind that whenever you are moving coil, either you are moving the magnet towards this or you are moving the other one. Now, if you are moving this away from the magnet, you expect what? As I'm moving this away, that means I'm reducing what? I'm reducing the kind of flux linkage between these two. As a result of that, I'm going to expect what? A kind of look at this. The arrow is just what you need to focus on. It's a simple question. Arrow here means south. And if south is produced at one end, the other end will produce what? North. So that is just that. The question says induced current will be generated so as to oppose the direction of what? The one that is here. That is south pole is here. The opposition of the current to the what? Opposite of south pole is north pole. So at the bar end of Y here, you expect a north pole. Whereby at the what? At the coil here, you expect a south pole. So induced current is produced, which produce south at the coil and north at the. So always keep that at the back of your mind. It's so simple. And the answer to this is just at Y here, the answer will be equals to what? Y is the north pole. That's the correct answer to this question. Always keep it in mind. South is clockwise, north is anti-clockwise. If I move it close to it, the flux linkage will increase. If I move it away from it, the flux linkage will decrease. Direction of induced current is always what? According to the rotation of the coil. If I move this close to it, then the rotation of this thing is what? I'm going to have what? The kind of what? Increase in flux. Increase in flux will produce opposite direction. Opposite direction, that's induced current or induced EMF. And the direction of induced current is always opposing what? the first current that is generated inside the core. So if the core is having a source, the induced current will go in the opposite of what was being produced. And this is the theory, basic theory of electromagnetic induction for basic level. Now the next question. Says a closed coil of wire is placed near a magnet. This is just the same thing again. The magnet lies along the axis of the coil. As you can see here, this is a very good diagram to explain. Under which of the following condition will there be no current in the coil? When the coil is moved toward, whenever you move any one of them, there will be what induced current, which will always produce an opposing what? It will always oppose the direction of the current. If current is flowing clockwise in the coil, it will produce what? Opposite to that. If it is flowing anti-clockwise, it will produce opposite to that. So that is what we call induced current or induced EMF. They always move in such a way to oppose the current. Whenever there is a relative motion or a cut in the magnetic flux, when there is a cut, the induced current always moves so as to oppose the chain producing. So it's always moving opposite to that of the coil or that of the magnet. This is the logic we use to get the direction of the induced current. Now, when the coil is moving away from the stationary now, whenever you are moving, you always expect flux to increase. And flux increases as a result of what? Increase in magnetic field and the area. We are still going to talk about other factors, and we are going to write the mathematical interpretation of this very soon. Now, this is also going to generate what? Induced current or induced EMF. Whenever you move either the coil or the magnet, induced EMF. When the coil is stationary or the magnet is moved, this is also going to work. Whenever there is a movement, there is relative motion or a cut in relative motion, induced EMF, induced current is going to be generated. This is the basis of electromagnetic induction. Now, this one says, when will there be no current? That is when both of them are held stationary. When the coil and the magnet are held stationary, is the question answer, because when you bring what? We said cross linkage only occur when there's relative motion. So when both of them are stationary, induced EMF is not going to be produced. Induced current is not going to be produced. So always keep that at the back of your mind, and that is the interpretation. When the coil is stationary but the magnet is not away, this is also going to produce what? An induced current or induced EMF. Lenz has told us that the direction of induced current is what? The direction of induced current moves in such a way so as to oppose the chain producing it. Now, from this Faraday law of electromagnetic induction called EMI, we can say that we can also write, he said, whenever there's a chain, that's the cut in the relative motion, EMF or induced current is induced, which is proportional to the rate. So that means the EMF generated is proportional to the rate of change of flux. The rate of change of something is what flux is amplified by dt. So when you introduce a constant, in fact, we write it in modulo form. Say E is now equals to. Now we write this as N, whereby N is talking about the numbers of turns of the coil. You can see these are coils that are moving in turns. So we say N the phi by dt. This is the mathematical entry in the interpretation for basic level. And we can write it in modulo because Lenz says the direction of the EMF generated is always opposite. So if you put negative sign here, you are very correct. So this is all what you just need to keep in mind, that what magnetic field generated or the magnetic flux generated is as a result of what? The change in relative motion between the magnet and the core. So this is the relative, or this is the simple way in which you can introduce it to electromagnetic induction. And I believe you understand this first example. Always use that term rule. In field, we produce anti-clockwise, out field, produce clockwise. In field, we produce anti-clockwise, which is north pole. Out field, we produce what? Clockwise, which is south pole. Keep that at the back of your mind. It should be very, very easy for you to pick what answers to the question. We move to the next question. Now, about the next question we have, which of the following devices in their common form would not function as a steady direct current? Now, let it be known that electromagnetic induction, we are talking about what? Induced current and induced EMF. So that means current is not flowing in one direction. So it is categorized under what we call alternating form of current. Alternating current. Magnetic effect of current force on the current carrying conductor and direct current. So alternating current, we have quite a lot of application, but for now, let's talk about what we call transformer. Transformer is one of what? Of the simplest application you can see, and please always keep that at the back of your mind. So we have Transformer, you can talk about dynamo, but keep it in mind, electric bell work on the principle of magnetic effect of current. We talked about it yesterday. Filament lamp work about heating effect of current. We've talked about Joule's heating effect. Transformer work on the principle of what? Electromagnetic induction, which is alternating current. Electromagnetic EMI induction. Let's write it in full now. So the answer to this is electric heating element works on what Joule's heating effect, which is heating effect of current. So electric bell, magnetic effect of current, filament lamp, heating effect of current, electric heating element, hot wire meter, all those stuff work on what heating effect of current. We've talked about this before. So the answer to our current, actual answer, the answer to our question is option C. So keep that in mind. So transformer work on the principle of electromagnetic induction. This is the next question. Now, the electromotive force obtained from a simple dynamo may be increased by dash. Other application apart from transformer is a dynamo. We can talk about what a dynamo does. A dynamo primarily converts, it's just what like a generator, a rectangular coil that converts mechanical energy, all right? Mechanical energy to electrical energy. Now, you know, yesterday I talked about rectangular coil under force of a current spanning conductor. You can take an illustration, just a quick one, just to for understanding's sake. I'm looking for what will make my work fast. I don't want to do. Let me just take a simple rectangular foot for quick explanation. We can talk about axis of rotation. To understand this concept video available, like you said. This video is enough for you to pass for exam. If you listen and you listen carefully to the details. Now, point is that as this thing rotates, you have talked from what simple harmonic motion as the rotation of this start rotating. Let me change to another marker. So it's moving at an angular speed of omega. You know that. We've talked about rotation and rotation. Now, yeah, it's going to be numbers of turns. Now, magnetic field is produced, which is always perpendicular. You know that magnetic fields is produced. We've talked about this yesterday. This is inward magnetic field. Now, according to what we have studied, according to the Faraday law of EMI, the law states that what the rate of change of loss is proportional. We talked about that. We say induced EMF is equals to negative n, right? A phi by dt, which is what we have just talked about. You can write in modular form because we are talking about direction. Now, listen, guys. Now, we should note that what another thing we can also talk about is that the rate of change as this thing is rotating like this. Now, it is rotating, you know that. So, we can say the EMF generated here is the same thing as the induced EMF generated there. Is, or let's say the flux. Don't let us go into EMF now. As this thing is rotating, there will be a numbers of what different type of flux. So the flux that is generated inside this triangular, I say triangular rectangular field, that is like a dynamo, just like a Lister generator for a very simple form of example, Igcse and now as this thing is rotating with its angular velocity, the flux linkage is now proportional. You can say to the numbers of turns, as you can see, and what the magnetic field, which can be what varies with time. The magnetic field and varies with time. Now, but for now, I can just tell you that it is proportional to what the total flux is proportional to the numbers of turns and the magnetic field in which this is what generating. And for you to know, this is rotating with what we have done simple harmonic motion, like I said, about its mean position or whatever, it's rotating angularly. So that is why we talk about angular velocity. From the equation of simple harmonic motion, you know it very well, which you guys know very well, that y equals to a sine omega t, right? So on substitution, if you put this here, flux is equals to n. When you put this and you cross multiply, we can now say, keep it in mind, you know, you have talked about it is also rotating angularly. So we can say now, generally, there is an area here. Area covered when it is rotating. All these things are what you can do. We've talked about this yesterday. So if we talk about all the parameters, there's a number of turns. It is rotating and producing a magnetic field. And what's also what we have an area. So if we substitute all these parameters, we can say the EMF generated here in a what rectangular coil, it's rotating with angular velocity. We can say it's the same thing as the number of torque multiplied by the area covered as rotating, then the what magnetic field and the omega. I think it's one of the important formula you can also keep at the back of your mind for the induced EMF generated in a rectangular coil dynamo, for example. It's always equals to what NAB omega. I can derive this, but for now, I'm only trying to give you direct formula, which I think is good for you to just keep in mind. Omega is 2 pi f, we know that. Then we can say NB cos theta. When we differentiate the phi by the t, like I said, this thing is raining time. So people will write it as, in my textbook, you can see it as N the B by the t. So then cos theta. So if I differentiate cos theta, you know it will give me minus sin theta. And minus will cancel minus and substitution. And I have NAB omega sin theta. So which is 9 meters and angle. You always do the angle to be what? Sin theta. So all these things are what you need in A level for A level physics courses. But for now, you only need to keep it in mind like a dynamo rotating at an angular velocity omega can be related that the induced EMF generated is the number of turns, the area of the field, the magnetic field, and the angular velocity. So the EMF generated in the coil is proportional to this, and you understand that we've talked about that under magnetic effect of current. Talk about torque generated in in a kind of rotational rectangular coil. We say it is equals to 1 BENI. Remember that yesterday if you are following the series. So from now, we can answer this question with simple question. EMF generated in a simple dynamo depends on all these factors, increasing the cross-sectional area. Winding the coil on a soft iron so as to decrease the magnetic flux through the coil. Now, let me quickly talk about this because I think it is very, very important for you to understand this. Now, you want to increase the EMF of this. Now, when you wind the coil on a soft iron core, now, there is what we call heat loss. I'll talk about eddy current and some other heating effects. We'll get about how it is being minimized in transformer. The same thing in dynamo. Now, to avoid what we call the kind of back electromotive force. Back electromotive force. That is what we call what? Eddy current. Now, eddy current is defined as a kind of let's say a miniature means small, miniature current that is produced on a metal body, produced in a metal body. Which oppose the direction of current. So now, whenever you mount any rectangular coil on the frame, inside the frame, there's a kind of what? A kind of what? EMF that is generating, they be generated inside the loop. We have talked about there is no force on the what? On a closed loop. We've talked about that before. But EMF that is generated inside the closed is as a result of what? Different what? Currents that are starting what to establish inside the loop. These currents don't allow EMF that is produced outside the loop to exist. They intend to take what? To generate their own inside current. For a very good example of this, our natural current we talk about, we call eddy current. It's a very good example of microwave. For those of you, you know microwave very well. So inside the microwave, you put vegetable there because of what? The miniature current inside the microwave, they are going to cook the vegetable. So current being generated inside the loop of a rectangular coil and called eddy current. And this current always opposes. They are the one that reduce the amount of EMF that is supposed to be generated inside the rectangular coil or the dynamo, as the case may be. So they are just small currents, small EMF, induced current, bring about induced EMF. Induced EMF, bring about induced current. That's what we are talking about. So always keep it in mind that eddy current is just like a kind of back EMF or a small miniature current that is produced inside the metal body. It is always like that. That is the definition I can give you for O-level students, and I believe you should be able to get it. Now, my point is from here, if you want to reduce this back EMF, what we do is what? We now use a kind of what we call lamination of the coil. So that means you don't want, you are laminate. If you laminate something, guys, you know how to laminate. If you laminate, you are trying to make sure that what all these induced currents that or induced EMF that are generated inside this core are being what absorbed by the lamination. But how do you laminate? You use a soft iron coil. Soft iron. And you know, if induced current or induced EMF is generated, there will be what? A radiation of it. It will be radiated outside. And it, as it is radiated outside, you say it is being lost inside the dynamo or inside the transformer. So, but to avoid that kind of radiation of it, because immediately induced current is set in back EMF starts, which we call the current, very small miniature current, you expect the what? The radiation of it, which we have talked about what? According to Joe 18 effect, we call it dissipation. So the best way to reduce what this thing is what by using what a soft iron core, which we say you laminate the core of the coil. As you laminate the core with a soft iron core, what you are reducing its loss by eddy current, which is a small miniature current, and by the so doing, the EMF of the coil will be increased. What I'm saying in essence is winding the coil with a soft iron armature so as to decrease the magnetic flux through the coil. It's like you are trying to reduce the eddy current that's produced inside the core of the magnet. Now, another point, another form of heat loss we still talk about it is hysteresis. That is magnetic reversals. Now, inside the transformer, we use what? We use and what electromagnet. We don't use a permanent magnet because we want the magnetic of the poles to be able and gesticulating now. You can't see me. It's just a pity. Now, you don't want the pole. You don't want the pole to be fixed. You want them to be what? To easily attract and repel. You want the attraction and repulsion to occur so that what? When there is a cut, what? There will be an induced EMF and there will be an induced current. That will be flowing. EMF generated will be flowing because you have different tones. You have some tones at the primary in transformer and some tones at the secondary. So as you use a soft iron and you use an electromagnet with contemporary magnet, you are trying to reduce the kind of heat caused by hysteresis because hysteresis is if the magnet cannot turn. For example, when there is a south pole, the magnet should be able to what? Induce a north pole so that there will be what? You understand my point? So for reversals of what? Magnet. For magnet to reverse from one pole to another, you use a soft iron bar. When you are doing that, if there is no magnetic reversal in the core, then its loss will still be what? Generated. Because when the same polarity we attract, opposite polarity we attract. Unlike poles attract. And when there is attraction, you know what that means. So the flux linkage will be reduced. So to avoid attraction, so you want something that can be reversed easily. So if lost by hysteresis is just as a result of another one, I'm just talking around it now. Hysteresis. Spelling sometimes can be funny. That's why I'm taking my time on that. So it's just magnetic reversals. Reverse of what? Reversal of magnets. And how can you minimize it by using what we call temporary magnet? So I'm just trying to explain all these shorty things for you. Because the things that you need to actually pass your UTM your life very, very well. So there are many ways in which it can be lost in transformer and as well as dynamo. But these are the major one in form of dissipation, leads. So you use wire of low resistance. We've talked about that under the effect of currents. In form of eddy currents, you laminate the core. In form of electrolysis, you use temporary magnet. You can see the way I've opened it down in the short concept in what in milliseconds. So that's how to do that. We move to the next question. But before that, we have to put answer to this. So winding the ball on this one is also a way of producing high electromotive force, which is also correct. So we are looking at which electromotive force obtained from a single iron ore may be increased by dash. Now, increasing the cross-sectional area of the coil. Now, listen, this is very technical because we are talking about dynamo. Keep it in mind. Now, for dynamo, we said E equals to what? NAB omega. You can write it in any form. Your textbook is not writing it in the form in which I'm writing it. So definitely it can be ANB omega or omega N, whatever. I think it's so easy to write it as NAB omega. That is why I'm writing it is that. So keep it at the back of your mind. So please note that. Now, we want to increase the EMF of the dynamo, increasing the cross-sectional area of the coil. Now, if you increase the cross-sectional area of the coil, let me know, please. The cross-sectional area of the coil, we are talking about angular because it's rotating, it's converting mechanical energy to electrical energy. So that directly a dynamo electromotive force is said to be proportional to this. You can write it like this: N, I'm going to do the flux, it's proportional to N, P, and what? And the what? Omega. So please keep that in mind. The full formula is NAB omega. So area of the field does not have effect in EMF of the dynamo. So that is why this is wrong. Now, second one is winding the coil in a soft iron method so that it can decrease the magnetic flux. No, winding the coil in a soft iron method does not decrease the magnetic flux. It increases the flux. Please note that. So this is also a wrong statement. I told you about what back EMF. So lamination of the coil, this is what has been done. And when you do that, you are increasing the flux. When we increase the flux, we expect what? High electromotive flux. So this statement is wrong because it does not decrease. Look at the third one. Increasing the speed of rotation. What is speed of rotation? Omega. You can see. So flux, electromotive flux, which is proportional to what? The rate of change of flux. This is proportional to NP omega. So we can say electromotive force is also proportional to NP omega. So in full, we are saying A LAB omega. But directly for a dynamo, we categorize what they work because no matter how big or how small the area is, it is the rate at which the coil is rotating that determines the amount of electromotive force that is generated. So increasing the speed is very correct because we're talking about angular speed or angular velocity. So that's the answer to the question. Making the field magnets longer, the longevity of the length of what of the magnetic field does not have anything to do. Using low resistance copper coil. If you use low resistance copper, you are only what minimizing its loss by what dissipation. And if you are doing that, please keep that at the back of your mind. Here you want to increase the electromotive force. That you are only preventing what its loss by dissipation, and that is not applicable in the dynamo. More like it is applicable in the transformer. So the answer to the question is C. When you increase the speed, because electromotive force is direct proportional to angular speed or the axis of rotation. Always keep that in mind. The next question. Now, about the next question, we have to convert an alternating dynamo into direct dynamo. The dash is done. This is a simple question. We want to convert alternating current to direct current. It's a simple thing. We said in a direct current, we use a split ring. Now, you can say split ring, which you call commutator. So about here, we use what they call a slip ring. Slip. So if you want to convert alternating current AC to a direct current dynamo to this slip, you replace the slip ring with what? A split ring. This is under magnetic effect of current and force on the current carrying conductor. This is under electromagnetic induction. So a transformer will make use of this, whereby your magnetic relay or simple thing electric bell or your generator. Let's use generator because that is popular. We make use of what? This. So converting AC to DC is also called what? Rectification. That is what called rectification. Rectification of current. So I mean, if you are doing the other way and DC to AC, we call it amplification of current. So keep all this shorty concept in mind. Because you might be asked about this is AC to DC, and this is DC to AC. I actually understand that. And the answer to this will also be this. So that's the answer to that. Replace the split rings, split ring commutator, and that's the answer to the question. The next question. If a current carrying coil is mounted on the metal, the back EMF induced in the coil causes that. You can see back EMF is called what? Eddy current. Talk about that. So it's a simple question, and the back EMF always causes eddy current, and that is the answer to this question. Now, we can also take all these simple talk options and talk about the inductance. Now, we'll talk about inductance. For those of you that you have watched my concept, you've known what called inductance. Now, the property of inductance can be explained in two ways. A quick one, short concept, because I may not be able to talk about it again. I'll just make answer going forward. And that is why I'm taking myself time to explain. Now, under electromagnetic induction, we find what we call inductance. Inductance, I said there are in two ways. There's what we call self-inductance, and there's what we call a mutual inductance, shorty concept. I will not take it to A level stuff. I will only limit it with O level. And when we say self-induction or self-induction, because induction brings about inductance. We say it's a property by which a conductor or a coil opposes a change in current. When was just a property, just like we write language, in which a coil, we say a coil or what, a conductor opposes, does not allow, opposes changes. When it opposes changes in current in itself. So we call that self-induction. Then the other one we call mutual induction is defined the same definition, but this is defined for pairs. Is it pair of coil or pairs of coil? Pair of coils. That is, you have more than one coil. For example, what am I talking about now? We have talked about that for any coil carrying current I, for any coil that is carrying the current I in a magnetic field, magnetic field is what? B. We said the current I is proportional to the magnetic field. So if you have a coil, the coil are always like this, they can be wounded. Sorry about the way I'm wounding my own coil. You can see it's going like this, like this. So we are talking about this is a coil. Sometimes it is called a conductor. So the current being carried in the conductor is proportional to the magnetic field that is generated in it. And we've also talked that what the flux, but when coils are being wounded together, they have flux. The flux generated, which is 5, is also said to be proportional to magnetic field. Remember, flux is given from what Faraday as Faraday law of electromagnetic induction. We said the flux is given as N, the phi. I said flux. EMF, induced EMF, is given as N, the phi by dt. We've talked about that. So for inductance, that's property of an electric of the property of a coil, which opposes change in current in itself. It's called self-inductance. Whereby mutual inductance is only applicable for what? The pair of coils, that is, there are more than one coil. For self-inductance, that means there is no change in current. Current is constant. So when we talk about current being constant, we're talking about straight wire. I don't want to go to extend the iron level. I don't want to limit it to what we got. Now, we've talked about the magnetic field, the magnetic flux is equals to B times A. This is the popular formula we talked about under magnetic field. Now, here, when we say the flux is proportional to B, so we can also say the flux is proportional to current. Current is proportional to magnetic field. Magnetic flux is proportional to magnetic field. So we can also conclude that for any coil that is carrying a current that is placed in a magnetic field or that is generating a magnetic field, the amount of flux generated in it is also proportional to the current that is being produced in it. So when we introduce the constant, we now say flux is equals to L. This L is now called the self-inductance. I will say coefficient of inductance. So this L is now called the constant here we have introduced is called inductance, which is measured in N. So keep that at the back of your mind. So that is just shorty concept and leave it to you now. So always keep this formula in mind that what the flux generated by what induction coil is always equals to what the inductance multiplied by the current. So this is the formula we use. So by so doing, if we now go by what the amount when the current is now changing due to what its own point, when current now starts to change, as the current is changing, EMF will be induced. So when EMF is now induced, we say the EMF induced in an induction coil, this is a coil called induction coil, is now equals to the rate of change of flux, according to Faraday law. So if it is equal to the rate of change of flux, we now say it's now L divided by dt. So this formula is also important for some of you. If you see some question directly, which you can apply this formula to solve. So for an induction coil, we say L divided by dt. For what? For your transformer, we say N divided by dt. Keep that at the back of your mind. Rate of change of what? Self-induction, the I by dt. And L stands for what? The inductance that is measured in N. So when it is mutual, we are talking about pair of coil. There are more than what? More than one coil. one, the first coil, apologies about that. The first one can be placed just like what I've explained, carrying the current. Then the second coil is also placed like this, shorty concept. You just need it. That is why I'm just trying to explain all this stuff. Let's say it's going up and down, yeah, the direction of current. Now, because they are placed what this one is having an inductance of L1 and this is having an inductance of L2. I'm trying to make it very, very fast so that you can get it. I've done this question just so you understand what we call induction in an induction coil. Like from what we define, to say it's only applicable as a kind of mutual induction that will occur between these two. Now, the flux linkage, there will be a flux that will link the first one to the second. So we now say in this kind of situation, there is what we define upon the flux. The flux in the second inductor is now proportional to the current in the first inductor because there's a mutual agreement, they are sharing something like that, just like little bit of the chemistry. So we now define the flux in the second inductor is now equals to now write M. This M is now called mutual inductance. So shorty constant concept is very important for you to keep at the back of your mind. So on this, we now talk about the kind of mutual relationship between the two. So you can actually wind the coil in different way. So when you wind it in different way, you can have different type of work. There are lots of things you still need to know. You are not in A level classes now. That is why I only give you with respect to what is required in your syllabus. So keep that at the back of your mind because when you have this type of thing, we define another property we call what other mutual inductance. We define another property which I think I've done in what we call coupling factor because you can couple coils in different ways. Now, coupling factor, what is the coupling factor? Coupling factor is called K. So mutual inductance is also given as the coupling factor K under root of the first inductance L1, L2. It's also an important formula for some tough question you can come across. So this K is called coupling factor. It is always the coupling factor K is always between 0 and 1. Always note that it can be what between 0 and 1, the coupling factor. When it is 0, when you wind two coils, the first one is wind like this, and the second coil is also, let me just show you, is also wind on top of it. So this type of situation, we say the value of K is 0. But when it is wind horizontal, maybe one is winded like this, and the other one is now winded like this. We say the coupling factor is equals to what? Is equals to 1. So all these are a little bit of A level, but always keep it in mind. For pair of what? Pair of coil. We talk about mutual induction. For one coil, we talk about self-induction. It's just a property of a coil or a conductor that opposes the change in current in itself. And that's about that. So we can also connect inductor in series and in parallel. Maybe when we get to the next slide, if we see question that relates to that, we might try it and solve that. But let's move to the next slide because there is no time. Now, next question. The magnetic flux in a coil of 200 tons, number of tons N is 200. Changes at the rate of 0.08 Weber per second. Rate of that's the phi by the T. Already discussed is 0.08 Weber per second. Weber per second. Weber. So that's it's just W. The induced is not inducted. Induced EMF in the coil. We say induced EMF equals to negative N the phi by the T. According to Faraday law, it can be in modulo. I told you something about direction. So the direction of induced current is always opposite, according to Lenz's law. Lenz's law is based on what we use. We call it the same as conservation of energy. Let me just help you. Conservation of energy. Some question can ask you about that. Let's go work on the principle of conservation of energy, just like your Bernoulli principle as well. Now, we move. Now, here we say negative NDL, here EMF is now, what is N? 200 tons. Modulo means modulo of negative number is positive, so containing this one to positive because it's a modulo times the 5 by the T is 0.08. It's a simple question. Multiply this stuff together. That is going to give you 1.6, I guess. So that's just that 200 times 0.08. Put your answer in the comment section. If you, I think it should be 16 volts or 16.0. Confirm the answer. I think it should be 16. And that is the answer to the question. The next one. Next question is, what precautions should a manufacturer take to ensure that energy loss in transformer is minimized? Like I said, transformer consists of work on the principle of EMI. Transformer work on the principle of electromagnetic induction, which are said to go through time for your level one step up transformer and fuel or step down transformer. A step up transformer has more coil in the secondary than the primary. So the numbers of turns in secondary is greater than that of the primary. However, the step down transformer numbers of turns in primary is greater than that in secondary. This is just so the EMF inherited in the word in a transformer is generally given as the one in secondary over the one in primary is equal to the numbers of turns in secondary over the numbers of turns in primary, which is equal to the current in primary over the current in secondary. So please take this shorty formula. It's an important formula when you see me ringing a formula. I do tell my students in offline classes that is very, very important. So that's that. What precaution should be taken to ensure energy loss in transformer? The winding of transformer should be made of high resistance wire. How would you make it of high? You have talked about Joule, but it is proportional to what? I square RT. Now, if resistance is high, heating effect will be high. So loss of what? Energy will be what? High. That is the dissipation of heat. Joule's heating effect. Look at this. The core should be made of thin sheet of metal. That is lamination of core. So if you laminate core, you are preventing it loss by what? Back EMF because more miniature current and the current. Back EMF. Small miniature points. So these are the definition we give the points. So I think that is that we don't need to waste our time because no magnetic material should be used. You must use a magnet for magnetic reversal, hysteresis. No flux linking the primary with secondary should be or the sponsor. You can see I'm laughing because they make no sense. So understand concept so that questions will be very, very simple for you to solve. In sequence, we move to the next question. And in the next question, the transformer has the primary coils of with 500 tons and secondary coil with 2,500 tons, 2,500 tons. When the voltage input to the primary coil is around 20 volts, the output is that. We just talked about ES over EP is equals to NX over NP, which is IP over IS. Also note that the efficiency in transformer, standard question, is always efficiency work output over work input. Shorty concept multiplied by 100. Work input is the work that is done at the primary. The primary is called the mains. And I know my student very well. Place. Or you say power output over power input, anyhow you want to do it. So please keep that in mind. Means primary. So primary is mirror. Power is current times voltage. We are using power output over power input. Same. Power is what? Current times voltage. So please, mains is the primary. So this is the primary, input is primary. Secondary is the work that is done when the transformer is releasing what? Alternating current to various homes or various houses. I hope you are following. So this is a simple question. The primary coils NS are NP is 500. On simplification, you can say 500. Secondary turn is 2,500. I'm using the direct formula is equals to when the voltage in primary stage, we are looking for the voltage in secondary ES, EP is the other entrance. On simplification, here 1, here 5. 120 times 5. If I don't make mistake, it should be 600 volts. And that's the answer to that question. So keep that in mind. And that formula of transformer is very important. The next question is a current of primary coil of transformer is 1.5 amps. IP is not 1.5, it was 2.5 amps. Apology. If the coil has 50 turns in secondary, and it's 50, and has 50 turns, and secondary, that means MP is 50, there should be an omission, not most the academic team. I think they are tired because they have been working since the beginning. It's not easy, and we are almost getting to the end of the syllabus. Now, the primary is 50 and secondary is 250. So this there's an omission. If the coil has 50 turns, I think there should be in primary and 250 in secondary. The current in secondary, IS, is that. Direct application of the formula, I told you ES over EP equals to NS over NP equals to IP over NS. So use this last two to solve your question. NS over NP is equals to IP over IS. So on simplification, my dear students, this will give me NS is 250 divided by MP is 50, IP is 2.5, IS is what I'm looking for. Year 1, year 5. Year 1, year 2, I can pause. If you don't know how to pause, my dear students, pause multiply. My offline students already know this method of pausing. Year 1, year 2. So IS is nothing but what? 2. Because what I'm seeing here is 2.0 amps. So that should be the answer. None of this option is correct. And if I make any mistake, you can actually try it on your own. On trying it on your own, you can say 50 year 1, 50 year 5. So here you have 5. Okay, this is 2.5. This is not 25. 5 IS equals to 2.5. 2.5 times 2 should be the answer. So the answer is 2.0 amps in the secondary. So keep that at the back of your mind. So that's the answer to that. The next one. The next question. Now, the answer to that one is 2.0 amps. Please, you can confirm that. Please, I think there's an error in what was done, as in according to the nature of the question. And if there's a mistake in what I've done, please, you can confirm that from, but let's do it well again. I think if I have mistake, the numbers of turns in secondary is 250 and in primary is base 250 over 50 is 5. So I have 5 is equals to the numbers of turns in primary. IP is 2.5. IP is given to it as 2.5 over x. So on cross multiplication, I have 5x is equals to 2.5. I'm the one that did rubbish. S equals to 2.5 over 5. And see, that one sometimes shortcuts may not help you because I've made a mistake. Year 1, year 2, 1 over 2 is 4.5. So the answer is like yes. I did rubbish in my cross multiplication. I box that. So the answer is 0.5, and that is option B. Because the academic team are very correct with the question. So it is not 2.5 divided by 5. It is 5 divided by 2.5. So 5 divided by 2.5, 2.5 over 5, not 5 over 2.5. So it's not true. It is what? 1 over 2. And 1 over 3 is what? 4.5. So the answer is 0.5 to this question. So sorry about that. Let's go to the next set of questions. And the next set of questions is more or less like what we have studied now. I will say a transformer which can produce 8 volts from 240 AC supply. That's it. 240 means what? The primary. That is, primary, the transformer will supply a particular voltage for you. So efficiency, like I said, is always power output, or you say work output. Power output over what? Power input. It's very simple to do. Times 100. Now, your input is that place where your transformer is planted. So input is always the main. Please keep that at the back of your mind. Input is always the main. Apologies for all these ones for stopping my class. That thing is not even going. Please go away. Thank you. Now, here you can say power output pattern. The power input is the supply. The total supply from the transformer. The one that will come to your house may not be up to 240. Please note that because of what? It's loss. So when it starts coming to your house, the one that will give you life might be 220. So always note that power input is always bigger than power output. So when you are doing your transformer stuff, don't make mistake. Now, if the current in secondary, this secondary is 15 amps, calculate the current in primary. It's just the same thing as what we are doing. Efficiency is 80%. That's 80 is equals to, so look at this, power output. Power output is, I don't know power output. I want to write power is current times voltage. Current times voltage. Power input is also current times voltage times what? 100. And just showing you all steps. Just for you to guys to understand. So The current in this one is like secondary current. The one in the mains where the current is being supplied is the primary. So this guy is primary, this guy is primary, this guy is secondary, this guy is secondary. Be careful about that. Now, for me, it's so simple to do now. We are looking for the primary current. The secondary current is 15. See, 15 times the secondary voltage. See, the one that it produced was 8 to your house. So the one produced to your house will be very, very low. Over primary current is what I'm looking for, IP, times the one from the mains, that is the transformer itself, is what? 240. You multiply this by 100. So it depends on how you can solve your math. If you are the type that you know how to plot, very good. If you don't know how to plot, do it one by one. Look at me now. I can say as a beginner now, 80 equals to, I'll say 15 times 8. That's 120. I guess 8 times 5 is 40. I will write 0. I keep 4. 8 times 1, 8 plus 4, 12. Over, this is 240 IP times 100. Now, for somebody that now know how to plot, you can say 0, cancel 0. Now you can now write again. Look at the 80 beginner. Normally I won't solve like this one in the exam, but it's 120 times 10. That's 1,200 over 24. You can call this IPX if it is causing wahala for you. So now you can now cross multiply. On cross multiplication, you can say 80 times 24x is equals to 1,200. So someone that know how to cut, you can cut this one and this one. Or you say, make H your formula. H is what? 1,200. Calculator is on your screen that day over 80 times 24. You know, I have turned IP to X, which is what I'm looking for. So if you know how to cut, no problem. If you don't know how to cut, leave it. 12 can go in 24. You don't know. Write it as 120 divided by 24 times 8. Then you multiply 24 times. You can see I'm doing like building. 24 times 8 should give us 8 times 4, 32. I write 2, I carried 3. 8 times 2, 16. 16 plus 3 is 19. So it's like saying 120 divided by 192. Then this time I have to press calculator now. So if I do that, 120 divided by 192. So on simplification, I'm having something like 0.625. I told you my calculator is rubbish. My calculator is rubbish, so you can just cut. But if I want to cut here, this one will be better for me. Because I know 24 can go in 120. Or 12 can go here 2. 12 can go here. 12 can go in 120. 12 can go in 12. 120, 10. 2 here 1. 2 here 5. 5 over 8 is 0.625. You can see 5 over 8. This thing is 5 over 8. 5 over 8 is 0.625. So application is very important. Always know that what the one at the input is always primary. The one at the output is always secondary. So the answer to the question is a basic question, but at least you need to know basic question. My calculator will write it in node form. So there will always be something like M on top, and that M means 0.625. So the next question. The principle of operation of induction coil, I've explained that to you. Induced EMF, induced current, that is what? Electromagnetic induction, and that is what? Faraday law. So it's a very simple question. Induction coil, we've talked about it, those coils that is wounded across each other. We can talk about what? I told you, when there are more than one coil, we talk about mutual inductance. When it is one coil, you talk about self-inductance, as current pass from one point to another. So please keep that in mind. So anything induction coil, transformer, dynamo, AC dynamo, they work on the principle of Faraday law. And all this Faraday law is called electromagnetic induction. Let's keep it in mind. Now, last set of questions for today is 3. Now, very good. If two inductors of inductance, 3 elements, two inductance are measuring I know it in series. You can see I told you about this thing the other time. I said when we have let's say isolated inductor, because most of the questions are isolated inductor. Like inductor 1, this is the first one. And it's just a wire that is wounded. The first one is 3 early and it's connected in series with the second one, which is what 6 early. These are the 2 terminals. I'm just trying to show terminals. Apologies for my stuff. I started this it's rubbish as usual. So we have this is the second terminal. They are arranged in series. So the equivalent inductor, we can say inductor equivalent, is now what we call the first inductance plus the second one, L1, inductance are reading as and plus L2. Now, I told you this is isolated. For your level, you don't talk about their mutual inductance. But if it is not an isolated inductor, most questions nowadays are funny. Look, I can wind two coil, some coil. This is a simple thing in generator that you see. You guys know coil, the way it is being winded. Now, if I wound coil like this, look at this. You know they are more than they are not isolated now. Isolation means they are separated. And the second coil is now wounded. Look at the way I wounded the second one. If you watch, the direction of my winding is different from each other. Hope you can see. In this case now, it is not an isolated coil. I can say the total, if this one is L1 and this is L2, then say this. It will be L1 plus L2 because there will be mutual agreement between the two of them. Say minus 2M. But if this one too is not isolated and it is in the same direction, it will be L1 plus L2 plus what? 2M. What is 2M? The mutual inductance. I told you this one will supply current. Current that flows from this one will be supplied to this guy. So because of mutual, you are saying close to again. You know, there will be a mutual agreement between you and that guy. So this minus 2M is always the mutual agreement if they are not facing the same side. But if they are facing the same side, you add what? The two what? Because some question might give you, this question is a simple one on isolated distance. It's just equivalent. This is always there. So this you just add L1 plus L2. But in case they give you, if there is a mutual inductance and the mutual inductance is also what? 3L, you also multiply it by twice that. So this student, this is a simple question. What is L1? What is L2? 6. 3 plus 6 is equals to what? 9L. It's a very simple question. And 9 is simple as 9.0. Inductance are measured in L. Keep that in mind. If they are not in parallel, there is no mutual inductance when something is already in parallel. Look at it. If you are sitting in parallel with a girl in your class, you are not forming any kind of mutual relationship. You can see the first one and the second one. So there is no mutuality, just like let me use biology terms, between the two of them. So basically, if you have L1 and L2 for parallel arrangement, we say the equivalent inductance is 1 over L equals to what? 1 over L1 plus what? 1 over L2. Yeah, this one is the total, which we call equivalent. So series you add, parallel you want to put in 1 over, or my way is always L1, L2 over L1 plus L2. It's the same thing. If you are using this one, you are still in primary school. Let me give you an instance. If this one is 5N and this guy is 5N, you are going to say the equivalent is 1 over L. Equivalent means the total equals to 1 over 5 plus 1 over 5. What do you do? LCM. SCM is what? 5. 1 plus 1. I hope students know I can over 1 plus 1. That's 2 over 5. So what you have? 1 over L equals to 1 over 2 over 5. What will be L? Cross multiply. L will be what? Just interchange. It's what? 5 over 2. What's 5 over 2? 2.5 L. That's the equivalent. The total inductance in this. But for somebody that know my shortcut formula, product over sum, 5 and 5 will be 5 times 5 over what? 5 plus 5. What's 5 times 5? 25. 5 plus 5, 10. 25 over 10, 2.5 N. Anyone you are used to from the secondary school, you can always do that. So I said, no mutual inductance when they are connected in parallel, but there's always a mutual inductance when you are sitting next to a girl that is close to you. So the mutual inductance can be positive and can be negative. If the wire is wounded, if the coil is wounded in the same direction, you add it with it twice. You know, two of you are combining. That's why 2 is coming from. The revision are also available on the channel, but for now, these are quick revision. When they are read in series, your own is always isolated conductor 3 plus 6. If it is parallel, 1 over 3 plus 1 over 6 equals to 1 over the one you are preparing for. Keep it in mind. This is the way you solve all your questions. Next question, guys, is the energy stored in an inductor of 5 millihenry when a current of 6A is flowing through it. Now, keep it in mind as well that energy stored in inductor, shorty concept, is given as half Li squared. The equation is available on my channel if you want. In fact, we have all called total energy for A-level students. We call Q squared over 2C. But you guys don't need that because it is not, we are not talking about RLC or LC circuits, inductor and capacitor, inductor and LR circuits. For your level, just keep it. Energy stored in inductor is half Li squared. L is inductance, I is current. Let's solve this question. Remember, in physics, you have to convert. This is milli Henry. So milli means what? 5 times 10 raised to power minus 3. Milli is what? Minus 3. So 5 milli Henry is the same thing as 5 times 10 raised to power minus 3 Henry. So that is that. And the current I is given as what? 6 ampere. Let's solve the minus place. So energy is equals to 1 by 2 times, what's the N? That is 5 times 10 raised to power minus 3 times, hope you know I squared means you are multiplying 6 2 times. 6 times 6. On simplification, 2 can cut one of these 6, that is 3. 5 times 3 is 15. 15 times 6 is 90. So if you write 90 times 10 raised to power minus 3, energies are always measured in joule. 90 is the same 9 times 10 times 10 raised to power minus 3. This term is 10 raised to power 1. So you see that 9 times 10 raised to power 1 plus minus 3. 1 minus 3 is what? Minus 2. Standard form. So 90 times 10 raised to power minus 3, 9 times 10 raised to power minus 2 is 0.009. Anyhow, you see the answer, because this is something as what is 0.09. So we make out when the zeros before the number is going to be what? Minus. How many zeros? 2 zeros. So the answer is 9 times 10 raised to power minus 2 euros. And that's the answer to the one. The penultimate question, which means the last question. The last question for this electromagnetic induction chapter is carbon particle are used in carbon microphone because the simple question. I hope you guys have seen a microphone before. Now, there's a difference between a dynamo and a microphone. I told you a dynamo, shorty question. Dynamo converts electrical energy and mechanical energy generator, listed generator, to electrical energy by rotation. We answer a question on that. Now, there's a difference between a microphone, that's what I'm doing, because of some other question, and what we call telephone earpiece. Now, because a lot of them students do ask me how, they don't understand. A quick one, I'm not going to waste your time on this. Now, sound to electrical, electrical to sound. They are different things. Microphone, sound. Now, earpiece, electrical to sound. Then, microphone, sound to what? Electrical. Microphone converts sound energy to electrical energy. Be careful. Sound to what? Electrical. Whereby earpiece converts or telephone earpiece converts or electrical energy to what? To sound. Some people still make mistake on this. So don't go and make silly mistake in your exam to sound. These are important things you can keep in mind. I'm trying to cover all areas of the syllabus, and that's why I'm talking about all these stuff. Now, last question is talking about why do you have what? Carbon particle inside carbon, what? Inside microphone. It's so simple. I told you when I talk about the magnetic effect of current, inside the microphone, there's always a magnet and there's a direct thing. Now, what that does is what? It's a very simple thing. Now, when you speak to your microphone, I get it now. There is what? A kind of reaction in between the component of microphone. There's a diaphragm, which is the moving part. So the sound is being transmitted as a result of carbon particles. The carbon particles will bring all the sound together. As the resistance, for example, as I'm talking now, I'm going to have high pitch and low pitch. It's a pity you can't see me because my camera is not working. Now, when I have high pitch, now as the sound is going into the microphone, inside what? The component of microphone, there must be a carbon granule. Granule is spelled Granul. So that is the one that actually prevents all the air resistance. Resistance is the one that doesn't want the sound. The sound has been accommodated together. If there is air resistance, what happens? The sound will reduce. So the carbon granule is the one that actually try to make sure that all the resistances inside that is coming with the sound is now being is now being reduced. And it will pass the sound inside the diaphragm. So what that's done is it reduces the amount of pressure or the resistance that is formed inside the microphone. Always keep it in mind, because I produce the sound. Sound is going down to a microphone. As it's going to every microphone, you expect the sound to be reducing. But for the sound to circulate, the sound must be accommodated inside the granule, inside the diaphragm. And what the carbon particle does is to prevent all the air resistance due to a change in pressure of sound. The sound is traveling from one point to another. So the work of the carbon microphone, there's always a carbon granule. It's not to amplify sound, because carbon are not good conductor. No, carbon is not even a conductor. It's an insulator. The only carbon that is a conductor is the allotrope of carbon you guys call graphite. It's only graphite that can conduct. Their resistance changes with temperature. No. We are talking about what? Resistance of carbon parts. When you speak to a microphone, changes with what? The change in pressure. Because the pressure of sound is what? Is changing inside the microphone, the diaphragm of the microphone. So the resistance does not change with temperature, but resistance of carbon, resistance changes with pressure, as the resistance is what? Opposition to the flow of sound. So as the pressure is changing, the resistance is also what? Is changing. So carbon particles actually perform a kind of what that bring all the what? All the sound molecules together and pass them through what? The carbon granule. So that's the answer to this. This is D, and that is the right answer to this. Guys, that is where I'm going to stop this section. If you find anything interesting, like I always say, consider subscribing to the channel. Tomorrow is another day. We are moving towards simple alternating current. And I think I have maybe two or three more topics to go. I have simple alternating current. I have modern physics. I have conduction of electricity, and I have semiconductor. So these are the remaining topics I'm going to do by the grace of God. Before Tuesday next week, we should be able to finish with all the sections. Invite your friend, tell your friend to tell your friend. Bye for now, and do have a wonderful time. Thank you.